Hello, my name is Christina DiMarino. I'm an assistant professor at Virginia Tech, and we'll talk to you about the prototyping and evaluation of a high-speed 10,000 volt silicon carbide MOSFET power module with high scalability and system integration solutions. And this is a member-initiated project Route 2, and it's done in collaboration with the National Renewable Energy Laboratory and Wolfspeed. So the objective of this project is to evaluate the scalability, system integration, and reliability of a wire bondless 10,000 volt silicon carbide MOSFET power module. So shown at the right is one of the wire bondless 10 kV module prototypes, which has dimensions of 70 by 60 by 15 millimeters. In order to achieve such a compact module, we've also had to develop a unique field grading system for the electric field outside of the power module. This unique system interface allows for reduced electric field strength in the air outside the module, as well as avoids accretion clearance requirements by avoiding any exposed conductors. Shown here is what the final PCB gate driver assembly could look like, where above in the PCB, directly above the power module, is where these unique system interface techniques would be applied. This technology could have a tremendous impact on medium voltage systems, including increasing power density, enabling faster switching speed, increasing efficiency, and even improving reliability. To date, we've developed a few 10 kV silicon carbide MOSFET prototypes. We've explored various sintering techniques for bonding the large area DBA substrates, and we've developed and tested and validated the unique system interfacing scheme between the power module and the gate driver and PCB bus bar. Shown here is the bottom half of one of the 10 kV silicon carbide MOSFET modules, where you can see here the two 10 kV silicon carbide MOSFETs. They're in a half-bridge configuration. And we use sintered molybdenum posts instead of the wire bonds for the interconnect. And due to clean room shutdowns recently, we've switched from sintering these moly posts onto plated silver top side of the silicon carbide MOSFETs to using a conductive epoxy adhesive, which will directly bond the molybdenum posts to the existing aluminum metallization of the die. And that enables us to get good shear tests exceeding 25 megapascal, and so that's helped us to continue in fabricating modules even during the shutdowns. So once this bottom half is completed, once the molybdenum posts are attached, we then attach the top DBA substrate, and so the silicon carbide MOSFET is sandwiched between these two direct bonded aluminum substrates, shown here. This is one of the 10 kV prototypes, fully assembled, where it's got spring terminals for the interconnect, 3D printed housing, which allows us to develop a unique lid geometry for relieving the electric field outside the power module, and silicone gel encapsulant. In the initial prototype, which was built using dies that are functional but out of spec, we were able to get reasonable on-state on-resistance and leakage current. However, in the initial prototypes, we had some voiding in the encapsulation. That issue has since been resolved, and so we're looking forward to now moving on and fabricating 10 kV modules with 6 10,000 volt silicon carbide MOSFETs total. That's 3 silicon carbide MOSFETs in parallel per switch position, and this will be done to show the scalability of this type of power module package assembly. The second task is to look at the design and test the compact module to system interface for these 10 kV power modules. And so on the right, we show a 2D cross-section of a PCB, and the yellow is showing the FR4, and the top and bottom has copper traces. And when you apply 10,000 volts between these two traces, you see that the peak electric field strength in the air exceeds the 3 megavolt per meter limit of the air. And so what we've done is we've explored unique field grading optimization techniques to look at designing field grading plates that are internal to the FR4 And by doing this, we can draw the peak electric field inside the FR4, which has higher dielectric breakdown strength than the air. And you can see here from the electric field distribution plot shown here from FEA simulation that the electric field strength in the air has been reduced by almost half. And so in addition to the PCB, we also need to be mindful of the air gap that exists between the module and the PCB. And so because of this, the lid geometry actually plays a significant role in the electric field distribution in that air gap. The lid geometry here is shown as the purple line here. So this is a 2D cross-section of the 10 kV module where these are your spring terminals, the blue is the encapsulation, and the purple is the housing. And then we've identified here the air gaps that exist between the module and the PCB. And so as you can see from the electric field plot on the right, we have several instances, several areas where the peak electric field is getting close to the 3 megavolt per meter limit. And so by optimizing this lid together with the PCB, we're able to then create, further reduce the electric field strength in that air gap. And so we've taken what we've learned from that first version for the 2-die 10 kV module and have used that to improve the design for the 6-die 10,000 volt silicon carbide MOSFET power module, which is currently under development. And so with this version 2, the PCB itself alone has a PDIV, a partial discharge inception voltage, that exceeds 11 kilovolt RMS, and the PDIV of the module and PCB interface together exceeds 10 kV RMS. We're also working on refining the gate driver circuitry. So thus far, we've tested the gate driver with a 4 kV silicon IGBT up to 2.8 kilovolt with a maximum dV by dt of 85 volts per nanosecond. And we've also done some switching evaluation of this gate driver with a prototype 2-die 10 kV silicon carbide MOSFET module up to 2 kilovolt, and that was used to help tune the short circuit detection circuitry. In addition to looking at the electrostatic and electrical performance of this unique 10 kV power module, we're also interested in evaluating its reliability. In particular, a unique feature of this power module is the stacked DBA substrates that are done for the top and bottom substrate for the power module. This stacked substrate is done in order to relieve the electric field at the critical triple point that exists between the ceramic, the metal, and the external encapsulation. And so when evaluating the reliability, we wanted to focus on the reliability of the large area sintering technique that is needed to bond these two DBA substrates together. And so we're evaluating currently 2 sintering techniques. The first uses silver paste, which is screen printed and then dried on a DBA, and then the 2 DBAs are then sintered under pressure together. As you can see from the CSAM image, we do have some large voiding in the center of the large area sintering bond. And so we've also been evaluating another method which uses dried silver film, or preform, which is stamped onto one of the DBAs. The 2 DBAs are then put into a hot press and sintered under pressure. And as you can see from this lower CSAM, there is a significant reduction in the voiding compared to the paste method. And so we would like to now continue fabricating more samples, and we'll be evaluating their reliability using CSAM imaging under thermal cycling conditions from -55 to 200 degrees Celsius. So the future work is to fabricate more of these 10 kV half-bridge modules with 6 die total, 3 in parallel per switch position, to test the higher current capability of this type of package. We also want to switch this 6-die module beyond 5 kilovolt, and we want to evaluate the thermal cycling of these sinter DBA substrates and look at their failure and also perform failure analysis. Thank you.